Today is a very special guest lecturer from industry. His name is Peter Rinaldi. He worked for Port Authority for almost 40 years. And the presentation he's going to be giving today is on the redevelopment that took place after 9/11, the World Trade Center. Some of the content, I want to remind you that all of the lectures for this semester have been posted on the EG website, so you have access to those to review and preparing for the quizzes, as well as to go back and look at that information. These slides, however, because of the proprietary nature of some of the information in here, won't be posted to the website. So please give Mr. Rinaldi a round of applause.
Say that you don't know. My name is Peter Rinaldi. Thank you for the introduction. I'm an engineer. I'm actually a graduate of this institution. I hold an advanced degree from here in engineering. I'm a licensed professional engineer also, with over 40 years of experience, including managing some very large projects in the metropolitan area. But with that as a background, what I'd like to do is I'd like to use a project that I was involved in actually from the very beginning as a young engineer to a finality, and that's the building of the World Trade Center, the destruction of the World Trade Center, and then the recreation of it, rebuilding the World Trade Center. And not so much about the project and the stuff itself that you're going to see, but more I want to focus and try and use it as an example of the kinds of things engineers do and how they do things and how they think, of which at some point in your careers, when you graduate, you will be part of. So that's what it is. So please bear that in mind. I'm not trying to present the project as much as trying to introduce you to a little bit about what engineers do and where they come from and how they think. So we'll start with the World Trade Center complex, which at the time it was built by engineers, created, was the largest office complex in the world. It was also the largest and tallest and biggest buildings in the world at the time. So you have to think about that, the engineering and thought process that goes into doing something that hadn't been done before on such a large scale. Okay? It also involved one of the largest underground complexes ever constructed by human beings, okay? In Lower Manhattan. It was 10 acres of excavation from the street grid all the way down 75 feet to Manhattan bedrock. And that was done so as to be able to found the heaviest and largest buildings in the world on a solid foundation of Manhattan bedrock. And it was being done in the most crowded area in Lower Manhattan. And this shows you a little bit about what the underground looked like. There was a railroad that ran through the site. It was called the Hudson and Manhattan Railroad at the time. Many of you may know it as the PATH system. Okay? It's Port Authority Trans-Hudson that connects New Jersey to New York and Lower Manhattan and Midtown. And so in order to do that, and there was a subway running through the middle of the site, one line site, there was many buildings. Engineers came up with a process to be able to build a bathtub or a wall in place so they could excavate down right alongside of the Hudson River. This was done in Lower Manhattan. So they came up with a method called the Slurry Wall method, which is really a way of actually building a wall in place. You excavate down, fill it with a bentonite slurry, which holds the opening. I mean, think about it if you've ever been on the beach as a kid and you're digging in the sand, and you dig down, and all of a sudden you get to the water table or groundwater, and it keeps collapsing on you, right? It keeps falling in. Well, it's the same thing in any kind of a major dig, even in a crowded city like New York. And then what would happen is everything would cave in, and buildings and streets around you would fall in, and that was a concern. Plus, there was a lot of water. So we were able to build something in place, put a reinforcing cage in, pump concrete in, and they had this well-out panel. And they went around the whole site doing this. And before you know it, you had this slurry wall, what was called the Slurry Wall, and they began to excavate down to bedrock. And if you look here, you can see this is what it looked like some 50 years ago with the Hudson River right here and the old piers, old West Side Highway. And this is the beginnings of what was One World Trade Center being founded on bedrock. This is almost 75 feet down. These are the old Hudson and Manhattan tubes that were built around and opened around 1908. They were almost 7 years old at the time, and people are traveling right through this at the same time while all of this was going on. So it was a major feat to come up with this method to be able to do something like this. Now, you can see it started to change the skyline, but here's an engineering problem. You're digging and building the largest underground complex in the world. Okay, so you figured out how to do it, and you're working through it. What do you do with 10 acres of material 75 feet deep? You know, that's a lot of material, right? So you're going to truck it out of Lower Manhattan and where? So engineers came up with the idea, and they said, okay, let's make that a problem into an asset. We'll go across the street where the Hudson River is, we'll build a little retaining structure of some kind, and we'll bring the fill over there. And lo and behold, that's what they did. So they solved the problem, and not only that, that became the land that is now Battery Park City in Lower Manhattan. So taking a problem, critical thinking, okay, and coming up with a solution that also involves economic thinking, right? You got to think. Economics always enters into a lot of things engineers do. Because if you have untold resources of money, you can do almost anything. But someone always has a budget. You even have a budget, right? You have limited resources, so you try and use those effectively and efficiently, right? Same thing, that's what engineers do. So this was a way to solve a problem effectively and efficiently. And so the buildings were completed. 50,000 people a day worked in those buildings. My office was on the 72nd floor in Tower 1 in those buildings. I spent my career there. I helped build the buildings initially, and then I worked my full-time there for my whole career until the buildings were hit by 2 planes on September 11, 2001, when some of you were probably about that date. Some of you may not have existed. So in your history, it's just distant, almost ancient history. But plane flew into the north tower of the building, and a plane flew into the south tower. This is a graphic that shows how a plane flew into the north tower. I won't go into the details, but it was the buildings were adequately designed that the impact of the plane didn't knock the buildings over. Okay. As a matter of fact, the buildings were designed structurally for the impact of the plane because in the 1950s, a World War II bomber flew into the Empire State Building. So when engineers were looking at this building, they thought, okay, a plane could hit it, let's design the building for the impact of the plane. What they didn't take into account and never thought of was in the modern jet age, the amount of jet fuel that is in a plane. And when that ignited and burned, it softened the steel in the buildings, and eventually they lost their structural strength and the building pancaked down, and that's what happened. So what looked like this on the morning of September 11th looked like this right after that. And this is one of the worlds that I came into. You can see this is where the outline of the Slurry Wall, the basement that I told you, this is the entire site. Here was building 1 that you saw in the construction, building 2. There was the whole PAD system station was rebuilt under the New World Trade Center. And so this is what it looked like. And then there was an issue very early on about not only was there damage to the site, but all the buildings around Lower Manhattan may have were damaged, or could have been damaged. The whole area was shut down. So engineers were tasked with immediately coming in and inspecting all the buildings, around 430 buildings in less than 2 weeks, to ascertain whether they were hackable or not. Very important. Why was it so important to get that area opened again? Because the financial capital of the world is located at Wall Street, right? And so when the market shut down, the trading shut down, so it has a worldwide economic impact. So engineers can impact things in different ways. So we had a team of engineers that went out. It's not important what they found, but we color-coded it and we opened this back up, and the buildings were, and the Wall Street was back in operation several days after 9/11, which was amazing. And so this is the scene that I encountered on the site. I was one of the engineers in charge of providing technical support to the police and fire that were doing the search and rescue. And I was also tasked with leading the effort to demolish and remove the debris from the Trade Center site. So that's one of the roles that I played there. So I led a large engineering team doing that. So you arrive, this is what you're encountered with. There's 100 feet of burning debris, people scrambling all over the place. What's the first thing you do? chaos. So what are engineers good at? Thinking and planning, right? Anytime you have a problem, you think, well, how am I going to solve it? What am I going to do? So the first thing we did was we said, okay, it's chaos, let's divide the site into 4 quadrants. It's not important what these quadrants are, but they're names of contractors and stuff that supply support. And we had teams of engineers that were assigned to each one of these sections of the site to provide analysis sections, engineering support. But the idea here is you have a problem, engineers don't throw their hands up. What they do is they think and say, okay, how am I going to solve it, whatever it is. Here was coming up with just a quick management plan, very simple, but effective, and no one else was doing it. And then, whenever you have a problem or something to solve or a project or a task, you want to gather information, right? Engineers need information. I'm always asking questions. So you want me to do this? What about this, this, and this? Well, I need this information. Even if you undertake a project, right? You're gathering information for your project. Here, we start to gather information because there was this big pile of burning debris above. But remember, I told you the largest underground complex in the world was below there, and no one was looking there. But the engineers said, okay, let's do that. So we started going underground and inspecting to gather information, okay? And we started going under areas. That's me when I had a mustache and I was a little bit younger a few years ago. Actually going down and doing some inspections and leading the teams. One of the things I found that when you want to do things, you lead by doing yourself. So sometimes, it's not always telling people what to do, but sometimes leadership involves you actually leading and doing things. So, and we were interested in, it was, 1,500 cars parked below there. There was all kinds of cars. There was critical communication cables that were traveling through there. We found areas that would collapse and not collapse. A large void where the slurry wall was being held up by the floors. It was damaged and the support, it was in danger of collapsing. We found and inspected, I remember going in here, floating in with emergency personnel on a raft to inspect the train station that was there, the PATH station. And we found a train was left there in the station, had been evacuated. So just remember this picture because I'm going to come back to it on those train cars that were left there. And then when you gather information, you have to assemble it and put it in some kind of a useful form, whatever the problem is that you're going to solve, right? And you're spreading information. So in this case, we start to ascertain what the different conditions were on different levels below ground so we could get a picture, and we put it on drawings. That's how we, so if this was one level and it showed pink with areas that were collapsed, areas that weren't collapsed, areas that were semi-collapsed and damaged, and we were able to get a 3D picture on drawings that we could use. Now, why was that important? Because there was a lot of people and equipment and things going on up above. And it was very dangerous because they thought the ground was solid with all these pieces of heavy equipment and people, and it wasn't. In some areas, it was very dangerous. So we had to make sure that some of the largest cranes and equipment and people didn't collapse into the underground and get hurt. So that was the problem we were trying to solve, and we were gathering information so that we could solve that problem and make it safe for people that were operating on the site. So just an example of the thought process that went into doing that. Now here's an example. The Hudson River flows down right over here near the tip of Manhattan. That's where the Trade Center was constructed. It had a deep basement. The PATH tunnel, the tunnel came in from New Jersey, the PATH system. It flooded with water and completely filled with water from the broken water mains and the firefighting equipment. And then we were concerned that happened, that if the wall collapsed, that wall that was built in the 1960s, holding back the Hudson River, that the water from the river would flow in uncontrollably into that basement, fill it up. And on the Jersey side, the Exchange Place station is 20 feet lower than the New York side. So which way does water flow? Downhill, right? So it would flood there. So not only would it do that, but it would flood over here. Then it would connect to the uptown tunnel that goes to Christopher Street, flood that because it's all below the level of the Hudson River, hydrostatic pressure. Then it would go over to 14th Street, and there it would connect because there's a connection to the New York City transit system, and it would flood the transit system all the way down to the lower Manhattan. and the whole system would be filled with water, flooded totally. So that was the scenario in September of 2001 that we were faced with as engineers, and the real danger that that could happen. So you're the engineer in charge, and you're thinking, you're leading it. What do you do? What was that?
Plan.
Plan? Yeah, what are you going to plan to do? Big pumps? Uncontrollable, unbelievable. A lot of water coming in. So you have to come up with a solution. Sometimes the solution is the simplest. You got a big pipe that's a tunnel. It's going to be filled with water. It's going to be flowing. You want to stop that from happening. What do? A big straw. How about you just plug it up? Right? Plug it up. So yes, that's what it did. We decided to go on the Jersey side and plug it up. So, okay, so you put a plug in there. Now, you're the engineer, you're going to say, plug it up. So the person who's going to do the work, the team says, okay, how big do I make the plug? Well, you got to plug up the whole thing, right? So the water doesn't flow through. Well, do I make that plug of the whole thing? Do I make it this deep? 1 foot deep? The tunnel is a mile long. Do I pour a mile of concrete into the tunnel to make sure that it doesn't flood from the water that might come in, the hydrostatic pressure or whatever? So, I don't know. How do you figure that out? Well, Google it. We'll talk about Google a little later about that, how it affects your life. But no, you'll actually got the tools to do something like that here. You know, you learn physics, you learn hydraulics, you know that there's water pressure, and you know that, okay, if the river is this high, I know that I can figure out at 62.4 pounds per cubic foot every foot, I can figure out a pressure diagram, and then I can impose that pressure diagram against the area of the tunnel, and I can come up with a force. Right? Now I have a force. How do I resist that force? Well, I've got concrete. How much did I put in? And I know the force is so big. I know that concrete weighs so much, but that's not going to do it. But then I know the property of how it adheres and what its adherent bonding strength is. So knowing those things, I'm able to figure that out and come up with a solution. So I can actually engineer something or a problem that's not a textbook problem, but the tools come from engineering school and learning about physics and hydraulics and math and all of those formulas and things that you'll be learning and applying. So that's what engineering is. It really is applied science, right? That's all it is. It's applied science with a little bit of economics thrown in, so you're trying to be practical about things. So we did that. How big do you think it was? Did we fill up the whole tunnel? Because you know why? You want to come back in and use that tunnel again, right? Concrete is very hard to get out. So we found that 17 feet. So we put a 17-foot plug in. And later on, taking out the 17 feet of concrete when we opened up the tunnels again was very difficult to take out. So imagine if you filled up the whole tunnel, which would have been the obvious solution. Just fill up the whole thing. Well, then you would have abandoned it. And you'll see that that wasn't a good thing to do. So in February, we started to get down back to the future to what it looked like back in 1968. And lo and behold, we got down to the train station and we found the train cars that were there. We exposed them. And so I had an idea, and I thought that it might be a good idea to save 2 of the cars that were in pristine condition. They had been, I say pristine, they had been damaged, but I said, you know what, let's save those cars. I actually thought about that when I first encountered them, but back in September, early time, but I never thought how we would ever get them out. But lo and behold, we got daylight and we decided, let's do that, so we were able to pull those 2 train cars out and save them. Now, even doing something like that requires some engineering. Why? Train cars are not made to be lifted up, right? They ride on tracks. Right? So if you go to lift it up, what's going to happen to it? It's not made to be lifted. It's going to bend, fall, to do all kinds of things. So we actually analyzed the geometry, the weight, the physical characteristics of the car to come up with points where you could lift it, where those points would balance the forces perfectly so they would be in sync so you wouldn't bend the car. A little bit of engineering. Just went into something that simple, okay? Okay, physics, weight, gravity, those types of things, you know, and Those cars are now actually on display at two museums, one in Connecticut and one in New York. I didn't know that at the time, but that just happened a couple of years ago. But there were a lot of artifacts that were being gathered at that point, so that's why I thought the cars would be something. We got involved in collecting things at the site and saving them, not knowing what was going to happen, but a lot of those are now on display in the 9/11 Museum. One of those artifacts that we gathered was a sphere that was a piece of sculpture called the Koenig sculpture that got partially destroyed in the collapse. We removed it off site, and then in January of 2002, then Mayor Bloomberg said he wanted an interim memorial to be built, and he wanted to use the sphere, so we had to take it and get it, rescue it back from Kennedy Airport where it was stored, and start to put it back together and build a mount, and we were going to mount it. So here's another engineering problem. When the sculptor designed this 30-ton plus sculpture, it was perfectly balanced and concentric, and the center of gravity came down through the middle. So it means, like, if I just put it on a little support, it just sat right on it because the center of gravity was perfectly balanced. Now, I take chunks out of it, it's damaged, it's not perfectly centered. So now it's got to do this because one side's not balancing the other side, so it's going to tip over. Well, if it's going to tip over and I'm going to put it on the ground, I don't want it to tip over, so now I have to figure out how to hold it from tipping over, right? So then I have to figure out, I have to engineer something that's going to hold it up. Well, what are the forces and what's making it tip over? How do they figure that out? So, well, I know if I pick up a body and let it rotate, it rotates to its center of gravity. Okay? So we did, we picked it up and the thing just rotated and stopped, and then it found its center of gravity and stopped. So now, how far off is the center of gravity to the new center of gravity? How do I figure that out? We use a very sophisticated tool called a protractor. Exactly. So, by using that sophisticated tool, literally, we could just measure the angle, and then by knowing angle, I can figure out force vectors and all those things you learn in physics and forces and so forth. And I can figure out the forces I have to resist, and then I can go through doing that. So, critical thinking. And here it is. This is that's the sculptor who built it. He actually came from Germany. It was a German sculpture, and we put it in place temporarily. It's now on permanent display at the World Trade Center site. But this was a very proud moment for him and for the people that put it together and for the engineers that were involved in something like this. So you think you can pick out who the construction workers are and who the engineers are? That guy's an engineer. Look at him. He's pretty geeky. He's got a slide rule, a calculator, and everything there. Right? Maybe he's not so geeky. So anyway, it was just interesting to do even something like that, engineering thought that goes into little things like that, okay? Critical thinking, to think that way, okay? And then it was put together, and that's what it looks like. And then we engineered the site down to where it was ready to be redeveloped. And in the meantime, we said, remember those tunnels that were flooded and we plugged up? Well, it was time to think about returning those tunnels to operation and taking a look at how damaged they were, because 1/3 of the people that worked in Lower Manhattan actually came through those tunnels prior to 9/11. So it was an important transportation link. Okay, so engineers got involved in restoring that link. We went in, we took the plug out. I was with the chief engineer of the Port Authority when we decided it was safe enough to take the plug out, so that was another discussion. But we then went in, inspected it, found that the old cast iron rings that were 100 years old, the structure of the tunnel was okay, but the infrastructure of the tunnel was not. All that flooding and water that had gotten in there and stuff had compromised the track beds, but also the communications and signal systems. And railroads run on signal systems. If you've ever been on the subway and you say signal problems, right, and you're sitting there and it's not moving, because signals are critical. They're the stoplights of trains, They're very critical. So all of that, the power systems. So we demolished the whole inside and rebuilt it all the way. Put it back in there. And then after rebuilding it, engineers get involved. Even when you do something, you want to test it or inspect it. So engineers get very much involved in inspecting things and testing things, no matter what that is, even software, right? New software, right? You write a program, you can test it out. Get all the bugs out of it or whatever. So here, we're doing some these electrical engineers going through testing the signal systems, okay, making sure that those critical systems work. So engineers get involved in doing that too, on all different scales. And then the temporary path station opened within 18 months, which was a feat because it brought back transportation. And then the thought about what was going to be built in the site. So engineers started to get involved in planning and thinking and providing support. A lot of times it's the politicians that get involved in doing things, but the practical aspects about, well, you know, how are you going to do it? How much are things going to cost? How long is it going to take to do whatever it is we're doing? You know, no matter what your project is. Usually engineers are providing that critical information. You know, you become the expert. So one of the first things we looked at was a new transportation hub to link all the transportation elements in Lower Manhattan there together. There was a pad system, there was a ferry system. There were 3 subway lines running through the site. You know, there was, in the Trade Center complex, 100,000 people a day just came through the transportation networks that connected through underground through the building. 50,000 people in the buildings, and another 100,000 just coming through the transportation networks. So it was decided to build a state-of-the-art transportation hub, something that would connect underground, the pad system, have a hall in the middle that would also have some retail and connect the subways, and would also have a connector that would connect the Battery Park City and the ferry system, and this is what the proposal started to look like. So it was developed by a fellow named Santiago Calatrava, who was a Spanish architect engineer. Let me see if I can get this to go back. All right, so see if this works. Sometimes when you have an idea and a solution, you need to come up and present it and convince people of what to do, okay? No matter what that is that you're developing. And here, what Santiago did and his team of engineers actually was develop a video to show what this might look like in his proposal. So with the light coming through around these, as the light changed on 9/11, this would be the transit hall which would connect. You'd have a skylight on the top that would open. On 9/11 it would open, let in light. You can see the shadows changing here. The great transit hall would connect with the subways. Here is the R line over here, so you have a subway connection. So you'll be able to get to the R, I guess the W line, through the pad control system. Be able to come right down to another level, go through it past to connect to the buildings that were going to be built on the site. The one subway which ran through the middle of the site, which I showed you previously, make a connection to that, and the tracks to pad control. Then the new pad station, you go down, steps, turn around, continue down. A new open-air hub, transit hub, escalators, a connection, a pedestrian connection that would go to Battery Park and the ferry terminal over there. Escalators and stairs that would go down to the tracks, to the path system, and connected to new platforms. So all of this was sketched out in a proposal. Light this so it lights up at night. And Calatrava's idea for this, he based this shape and the look on his idea of a set of doves flying. So that was kind of his architectural concept. So the point here is if you have an idea, whatever that idea is, many times you have to present it, and then you have to take that idea and maybe bring it to reality. So engineers do that. They take ideas, solve problems, and then bring it to reality. So here you can start to see the reality of that starting to develop here. Okay? And the structure and the shape that you saw in that cartoon video, which was the idea of presenting it, actually now coming to fruition. Okay? Things that engineers do. And there's a lot that goes into something like this. You can see the skylight going. The shape that we showed you before, it's taking shape and get out of the ground. The inside, give you an idea of the scale. You can see the idea of the scale of this. If you haven't been to Lower Manhattan and seen the structure, it's a very striking piece of architectural engineering. And this is what it looks like with the transportation hub. And while that was opening, many times when you're doing something, you have to do it in stages, which means that, you know, everyone wants to get things back to normal as fast as possible. So in this case, engineers, we actually engineered that this wall you see here, the station was partially open, and this wall is this wall. So on the other side, construction and building of part of the station is still going on, while the other station is in use. And you can see this below ground, right next door, there's active escalators and trains, and right next door to it, there's still construction, so you're able to bring that to fruition. So whenever you have a problem to solve, sometimes time becomes part of that consideration too, so you have to move things along. This was the pedestrian connection. Here's the sketch of what it looked like. This goes to Battery Park. This is what it looked like in actuality when it was completed. A lot of the stone actually was cut over in Italy. Every individual piece was cut over, measured, and brought over here and then put together. So that was even engineered in doing something like that. And then the memorial, the concept and the idea for the memorial in terms of building the pools, the memorial park, you can see the construction going on, and the whole underground complex. So part of that underground complex, that was the original World Trade Center, is now part of the memorial complex, okay? The underground memorial as well as the memorial up above, where you can go down and see the bases of the buildings. You can see the artifacts, some of the artifacts that were collected there. And then returning the buildings that were there. Remember the original One World Trade Center. So the planning and doing that. So a new modern office building was being designed and built on the site with new high-tech security measures also, new types of elevator controls, new types of lighting controls, stuff that hadn't been done before in the past. You can see the foundation starting to go in and the building starting to rise out of the ground. This is a good point just to talk to you a little bit about. A building is like this, a large building is a good example of that there's interdisciplinary contact that goes on when you're doing something like that. A building like this involves structural engineers, architects, mechanical engineers, electrical engineers, computer engineers, industrial engineers, all of that go into something like this. And in this building, for instance, the owner decided that they wanted to change the glass on the outside of the building, and they didn't want, they wanted full height windows. They need floor to ceiling so you can see all the way up. Well, if that design changed, architects said, no problem, we can do that. Well, then the mechanical engineer said, well, wait a minute, now I've got more glass area, I've got more heat load, I need more heating, I need cooling during the summer with the sun coming through there. So now I have to increase my HVAC systems. Electrical engineer says, wait a minute, I designed the power systems based on what we had before. Now I need more power because you're going to have bigger air conditioning and heating units. So now I have to put substations on the floors. Structural engineer says, whoa, wait a minute. I designed the floors already and it's not carrying these stuff. These things weigh too much. Now I got to change the building design. So, and they're all doing this. So there's someone called a project manager, okay, on any project, usually large projects or large undertakings. There's a project manager. He's kind of like the orchestra band, right, that kind of coordinates that. So, seeing something on project management, so in a large building like this, it's not only interdisciplinary, but you need an orchestra leader or a project manager. And that project manager is almost always an engineer, and it could be in any discipline of engineering that you become a project manager to lead projects. What's important in being a project manager is that you have good communication skills, problem-solving skills, okay? And that you know a little bit or understand a little bit about where the other disciplines are coming from, okay? So you may not think that's important, but it is important to know what your other fellow engineers are about in the other disciplines, just to have them. You don't have to be an electrical engineer to understand, substations and electrical systems, high voltage lines and stuff, but you do need to know enough about what they want and to question that. Okay, I was a project manager, then I was a program manager, then I was an assistant director of engineering. I had multidisciplinary engineers working for me on large projects. I always questioned them because I assigned all the drawings for them. But I always questioned them on certain things that I thought didn't make sense because I had a sense about something they're doing. I didn't tell them what size to make the circuits and stuff. But when electrical engineer says, I need a substation this big and your equipment's about half filling it up, I said, why do you need such a big building for just this amount of equipment? And then we have a discussion about high voltage switchgear and all of this stuff. So anyway, it's important to think about that. You may not like mechanical engineering, or electrical engineering, computer science, but try and understand if you want to get ahead in engineering. So here's the floor-to-ceiling glass I talked about, and you can see the building going up and being completed. And at the same time, we had other buildings on the site that had to be built. And remember, we now decided to make an east bathtub on the other side of where the original bathtub, because of the memorial. The memorial was being put where the buildings were, and now we had to move the office buildings to the other side. So some of these large office buildings now had to go to bedrock, so it's like going back to the future again in that engineers had to go back to what other engineers did before, and that's another point. You learn from your predecessors, okay? You learn from what comes before you, and you try and better it and go on from there. Okay, just don't ignore the past. Okay, don't ignore the past. You can learn a lot, from technology that went before. And in the middle of that, the subway line was running through here. So now the engineers were faced with the active subline, the one line running through the middle of this, and now we want to excavate all the way around, down like we did. But I got an active subway. People are traveling through this, so what do? Well, you say, shut it down. Nah, the MTA says you can't shut that down. There's thousands of people using it every day. So then you say, okay, you know what? All right, I'll work around it. So I'll come up with a way to work around you. I'll put some supports through your station, pick it up, hold it up, and I'll dig around under you, and you can fly through the air over my site. And that's what we did. You can see that here. You can see this is actually underpinned like this, and trains actually continued through. This thing was excavated another 50 feet below that and built up all while that was going on. So that was a problem, and engineers had to solve that. So they did. And you can see this is going down on that site, Back to the Future. And now we have, this is the rendering, and this is the buildings actually going up. And most of the buildings, except for one, are there in place. I'm going to see if I can get this working. But one of the things, many times when you're working on a very large, multidisciplinary project, in not only in the design phases, but then in the building phases of what that is, or the implementation phases, there could be a lot of conflict in terms of times and schedules and stuff of what's going on, especially when there's a lot of facets to it. Here, there were buildings going on, memorials going on, stations going on at the same time, and there was a lot of complex projects all being handled by multi-teams, so we needed to coordinate that. So we went to a 4D model. So 3D, what's the fourth dimension? Time. So we added time because time over it. And we took all those little individual, this is a very high roll-up, but if you did project management, each task has a little line, okay? Can you imagine millions of lines for different projects? You roll them up over time, and you get a picture of what was going on. So we just did this to know the time when the streets would be in, when the station would be coming up, when building one would be coming up, when the memorial would start, and when the other buildings would rise out of the ground. This is all accelerated, but it was a point in time that every point in time you could tell who was doing what. So this is a very high roll-up of millions of pieces of data, okay, and scheduled data that tells you what the build out would look when it's out. Now, these buildings are up, this building is up. This building it's going to go up in the future, but all of this is in place. And it's still under construction, the Trade Center complex, and engineers are still involved. This is what it looks like now. You see the buildings up, you can see the memorial in place, the transportation hub, 1 World Trade Center, 3 World Trade Center, 4 World Trade Center. So, and there's still work to be done on a performing arts center and another building. The last building to go up will be taller than the Empire State Building, just to give you an idea of size and complexity. A very complex project that will go on. So this is continuing. You can play around with the lighting sometimes, which we did during the construction of the buildings. And then you can get to the end, you might wonder what that is. That's gold. $3 billion worth of gold and silver was under the World Trade Center. Guess who found it? Guess who had to give it back? There was a bank vault under the Trade Center that was there, and in order to get to that bank vault, all the power was gone. We had to bring in temporary power because you could only get to through specialized elevators. So engineers that were there, some of my fellow engineers with electrical backgrounds, figured out a way to do that. It took 120 armored trucks around the clock for about 5 days to take out all the gold and silver bullion out of it under armed guard. So some interesting things that go on. But I'd like to talk about, just finish up on talk about what engineers do. I just tried to use this as an example. Obviously, you go to different facets of engineering. But some of the things you saw here in terms of the processes and thought processes and how you interact apply no matter what type of engineering you go in and what kind of project you undertake. It's the same. And engineers have a tremendous impact on how we live. Just think about it. This morning, I bet you got up. One of the first things you did was go in and turn a faucet on, get some water, right? Without thinking where that water comes from. I just take it for granted. Okay? It comes from as far as 100 miles away. And you can thank engineers that went before you that actually bring 1.5 billion gallons of fresh water every day by gravity to New York City. Okay? That's an engineering feat. Okay? You wouldn't be here without that water. You couldn't exist. 8 million people could not exist in New York City. And indeed, the reason that New York City grew the way it did is because of that fresh water. Otherwise, it wouldn't exist. So think about that. Also, I bet the first thing you did, though, is flip on a switch. And you flipped on that switch because you wanted light. Think about Thomas Alva Edison and his team of engineers over 100 years ago, okay? They lit up the first city in the world. You know where that city was? New York, right in Lower Manhattan. Think of where you would be without the engineering involved in electricity. Okay, any of you been around in a blackout, power outage? How does that feel? Think about it. Think how dependent you become on engineers for power and what that does. And now in your own lifetime, engineers have had a tremendous impact on you. How? I bet every one of you has a device you carry around with you every day without even thinking about it. Oh, what is that? How many of you don't have one of these? Very few. Steve Jobs and his teams of engineers, okay, have changed the way you live in your lifetime. Think about the impact of this. Think about it. Think about the socio-economic impact of having communication at your fingertips. Worldwide communication, right? You can share photos, you can share videos, you can share text, you can talk with people, you can look up the internet, you can research, you can do all of that in your fingertips. That didn't exist 10 years ago. Okay? Think of the impact it has on you. Have you seen the social impact, the political impact of instant videos across the world? How people organize? It's tremendous. I think this is the most impactful piece of engineering we've seen in 100 years, right here. Okay, this phone, think about it. And so that was done by engineers. So, somewhere out there, one of you might be the next Steve Jobs. So, stick with it, stay with it. We need you in the industry, whatever discipline of engineering you go in. There's a tremendous demand for engineers, okay, and technical talent. The one thing I would tell you is, whatever you do, make sure it's something you are interested in. Don't go into an area of engineering because you think it's going to pay more. That's not the way to go into your life's work. Okay? You need to be passionate about it. You need to be interested in it. There's nothing worse than doing something you're not interested in because you won't do it well. And that does not bode well for everyone else. So stay with it. And engineering is a good field economically, but it's also a good field technologically and rewarding. If you have any questions, I can answer them. If not, thank you for listening and good luck in your future. But any questions? What did I do with all the gold? I retired, that's what happened. Yes?
What happened to the, this is more of a World Trade Center question.
What happened
What happened to the radar that was originally supposed to be installed at the top of one World Trade Center?
The antenna?
No, like surrounding the antenna.
Ah, yes, there was a lot of discussion on the antenna that when I was asking about the antenna that went up on World Trade Center. Just so you know, One World Trade Center, the new building, is exactly the same height as the original building, 1,368 feet, and it goes up to 1,776 feet because of the large communication antenna. Originally, that antenna was going to be enshrouded in an architectural element, actually. And what happened was the cost of putting that on didn't warrant the go-ahead of the work that would be involved in putting that on. So that became an economic decision. Engineers figured out they could live without it would still work. And so it would look a little different, but that was why it wasn't built. It was really an economic decision. Also, it's difficult to construct 1,400 feet in the air. It was an expensive item. That's why it didn't go ahead. But there is a beautiful observation area on top of the Trade Center if you have $32. Economics. Cost, all these buildings cost a lot to operate. Especially, they mentioned, because we have a lot of security issues that we didn't have 20 years ago. Yes, question in the back.
So, did you mention about how another such attack could be like dealt with the best in the future with the current?
Good question. What do we do different? Well, engineers can't prevent planes from flying, right? I mean, that's not something under your control. Although you can design weapon systems that might keep them from flying into buildings. So, what we did is in engineering, whenever there's an event, a tragedy, or something breaks, or something happens, look at what the causes, and you try and say, okay, what caused it? How do I correct that from happening in the future? Here, we knew that the buildings collapsed from the fire, okay, partially when the planes flew in. The other thing is that we had some difficulty with people evacuating, even though they did get out. So, the steel, the core of the building is designed differently than the core of previous high-rise towers. The core is the center of the building, the core of a high-rise building. You walk through a building, you go across, and that's where all the elevators are. That's called the core, center of the building. And the Trade Center was made out of steel and plasterboard and concrete block. Very soft stuff. The new buildings are 5-foot thick, high-strength concrete, the core of the building. Okay, the strongest concrete ever used in the United States is in Building 1, One World Trade Center. Okay, high-strength concrete, 3 times stronger than any concrete that was used previously on it. So, if a plane hits there, what happens when the planes hit there? They demolish all the staircases that were in the core of the building. That's why people couldn't get out. Died. So we've changed that. We also changed what we call fireproofing. You have materials that burn like steel. Steel will burn. If it gets hot enough, it melts. It gets soft. So in buildings, you put in what you call fireproofing, okay, which supposedly what it does is it insulates the steel and keeps it from burning or melting until firefighters can get there and put out a fire. So what happened in the Trade Center is the planes flew through and they just shredded all the fireproofing off the steel. So now the fireproofing in the buildings now is 10 times stronger and more adherent than any fireproofing that had been used before. So, and the stairwells have been placed in such a way that there's duplication of stairs and they're out of harm's way. So those are some of the things that you can control as an engineer. You can engineer something to make things better and safer. You can't control terrorists getting on airplanes and stuff. That has to be done elsewhere. But you can actually make your building safer, or whatever it is you're doing that's under your control.
So basically, the World Trade Center project was the redevelopment of the World Trade Center site presented a unique opportunity to redevelop Lower Manhattan, etc., because you were kind of starting from scratch in a lot of things. Well, what do you think was the biggest missed opportunity in terms of development at the 9/11 Bay Area?
Biggest missed opportunity? I'm not sure I could answer that one. We put back the street grid, which was interesting and stuff, taken away, so we reintroduced that. I'm not sure I have an answer for you on what opportunity was missed. You know, I think a lot of thought went into going into planning it. Some people wanted the buildings built exactly where they were and the way they were. And some people didn't want anything built at all, just leave a big hole in the ground. And then compromise and sanity came in, and we came together with what I think was an opportunity for a good memorial and a meaningful redevelopment of the site. So, if anything, we missed the opportunity to do it faster. There's a lot of bickering and discussions going on. Not the engineering part of it, but the political, economic part of it. That's kind of what we missed. We could have done it faster.
You were worried about the subway tunnel flooding. Did you have to rebuild the Slur Wall or just fix it and reinforce it?
Yeah, the issue with the slurry wall, a good question, was, I didn't want to get into too much detail, but when the original trade center was built, there was temporary tiebacks put in that held the wall in place, anchored it to rock, and then they were abandoned because the floor system in the ground provided all the structural support around the site. When the buildings came down, the only thing actually holding the wall up was the actual pile of debris from the buildings, and in order to search that debris for people and remove it, it was holding the wall up, so we actually went back and installed tiebacks again, wall into rock, to hold it in place. And then when the building was finished, all the construction was finished, the tiebacks were no longer needed, they were temporary. If you go to the museum today, and the 9/11 Museum, and you go down into the Great Hall, you'll see a section of Slurry Wall that's exposed there, the original Slurry Wall, and you'll see the tieback heads there from what we did.
Any other questions?
All right, well, thank you. Good luck in your career. Stick with it.